Alright. So hi there, everyone. I'm Sanket Sharma, and today I'll be presenting high altitude non-GPS navigation, which was the GSOC project for this year. Oh, sorry. Okay. So we'll start again. Okay. So hi, I'm Sanket Sharma, and I'm presenting high altitude non-GPS navigation, which is a GSOC project for this year. So there's a problem with the mic.
To get it.
Oh, sorry.
Lift it up, boy.
Quite tall. Maybe try that.
All right. Maybe that will work.
Is that better?
I think that's it. Seems like.
There you go. Right?
All right.
Give it a try, a little test.
Hello. I think it's fine, right? Yeah. All right. So a bit about myself. So I'm a mechatronics graduate from India. I just graduated this year. I'm 22, and I've been GSOC contributor twice already. So in 2022, I was working for the updating ROS for ROS integration for the cartographer SLAM. And this year it is high altitude non-GPS navigation, which is a vision positioning system. So currently I'm working as a senior control system engineer at a defense startup in India. And also I'm a technical advisor for CUAV. So I think we should start. Okay. So overall, I'll be explaining what I did in this summer in the GSOC and what kind of positioning system we actually developed, plus some AI enhancements for this, so that the vision positioning system works irrespective if GPS is there or not. So let's start. Okay. So the task for this year's GSOC was to actually develop a reliable vision positioning system for UAVs to work in the GPS hidden areas, specifically at high altitude. If there's a, for example, loss of GPS, so at least the drone should not land. So let's assume a place the drone is far away from the home, and there's some GPS loss or some problem with the GPS. Generally, the drone will land automatically as a failsafe, but we don't know if the drone is over some water areas or something. So there should be a failsafe for that. Instead of landing at the place, it should come back to its home position, as close as to its home position, without the GPS. So it started as a RTL failsafe, but later on it actually became kind of a navigation system, as a standalone navigation system without GPS. So specifically, this thing will work specifically in case there is a loss of GPS mid-flight. Apart from that, there will be, if there's a high GPS interference during the flight, so it can take over as a main positioning system and a state estimation for that, and will obviously work for the Sentinel applications. So, but before starting out exactly how the algorithm, but why did I choose the vision positioning system? There are other positioning system irrespective of the GPS, like the Earth's magnetic field anomaly field anomalies based absolute positioning systems. But I think the vision positioning system is simple enough to start with to at least create a pipeline for the positioning system that does not rely on the GPS. Plus, it can achieve greater accuracy in case of very precise landing that depends upon some specific areas or the visuals of the areas. Can be added in as an extra help to the GPS for a very better state estimations. So over this GSOC, I implemented specifically three different kind of this vision positioning systems. So the first one is the SIFT feature matching. So before I start with the technology, technicals of that, I should give some kind of analogy so that everyone understand it. So let's assume we are in some kind of village, unknown village. We don't know how to enter. We have a map. We know the we know the exact position of entry where we enter in the village, and we stroll in the village for some time, and we kind of forget where we are right now. But fortunately, we have a map of that area. We take out the map, what we generally do, look around ourselves. Okay, I will look like there's on my right, there's a lake. On my left, there's a hill. And on front, there's a house. So generally, what I will do is take out my map and look for every kind of features on the map. Like, okay, I can see some kind of billboards over there or something like that. And I will see a specific area in the map that will match exactly the same thing. There's a lake, there's a hill, and there's a house in front. From the map, I will estimate, okay, I'm probably at this place specifically. If I just show from the image, that might give an idea. And because I know the entry point, because right now I estimate where I am, so I can easily go back outside where I started from. So that somehow I kind of localized myself based upon the features around myself. So this is localization. I'm localizing myself based on the map. So this is a similar analogy that has been used in the drones this time. So, what SIFT is, so scale invariant feature transform is similar thing. It detects the features in what the drone sees and what the map it has. And similar, it look for the features, match the features from the image to the map the drone stores. And it kind of localizes itself on that map without the requirement of the GPS. Obviously, because you have a map of the area, either it could be satellite image or it could be a map you created through surveys. So it enables the UAVs to estimate its position without the GPS by comparing the two images. So uh, there are some important parameters, some technical. I won't be repeating these all parameters because here. So these are majorly the EKF related parameters, specifically the vision positioning system VISO types and EKF flow based parameters, so as to adjust the measurement noise, because obviously in case of vision positioning system, the measurement noise will be really high. So we can obviously adjust and increase all these parameters. And again, the algorithm obviously includes some basic image pre-processing like color and geometric corrections, obviously. So now let's discuss the implementation, step by implementation, how this exactly works. So if I have an area where I know the drone going to transverse or drone going to actually fly, so I will generate a map by doing a simple survey, and I get multiple images of the area. I just join them through the SIFT algorithm, because what the SIFT do actually is extract the features from each image, not map the features. It extract the features, and there's a FLAN matcher, which is nothing but some sort of differential mathematical equations that through Euler distances finds out the matching between how the two images match, and it joins the homography, finds the homography and overlaps the image to create a map of the area. So once you have the map, you can put that map on the drone, and later on, when you have the map on the drone, so that will act as a reference point for the drone. So let's say the drone goes to a specific point in this flying area and it loses its GPS. So drone's gimbal, with pointing downward and stabilizing itself with downward, will start to capture the images. It will send it to the offboard computer. The offboard computer start to extract the features from the SIFT. It uses the FLAN to match those feature points from the image to the map that has been already been given. And it starts to estimate its position, because right now I know. So as in the image you can see here, this rectangle area is what the drone is currently seeing right now. This is just a single frame. And this is the map. The whole thing you're seeing, it's the map the drone already have. So if I know where I started from, because as an example analogy, village analogy, I know where I started from. I know right now from the center of pixel of the frame that where I am currently. I will match that. I will simply get the pixel values, and there's a very simple proportionality between the camera's intrinsic parameters and the real world coordinates, is that they are proportional to each other. The offset in the XY axis in the real world upon the height of the drone is proportional to the XY pixels distance in XY axis upon the focal length. We know the focal length. We know the pixel distance from this algorithm. We know the altitude through barometer. We can just plug in all those values and we can get the offset in the x-axis and y-axis in the meters or in centimeters. And that will help us to get the precise position of the drone. And we can send it through vision position estimation mapping messages to the drone, so that it can start to localize on based upon the local coordinate system. So overall, a lot of optimization is required in this thing, because SIFT inherently is very much, it takes a lot of processing. It takes a lot of compressing actually, because you need to compress the image so much so that at least I get the 4 hertz. That is the requirement for the EKF at least to stably estimate the state. So that's one of the major drawback for the SIFT part. But overall, if the compression and all these things went well, so I can get the 4 hertz minimum rate from the EKF and send the data over the vision position estimation, and I can localize the drone without the requirement of GPS. So a very basic example how I create the map. So this is the data set of images that has been taken from a survey, and I will just send that to SIFT, find the homography, overlap the image, and I can get a bigger map of the area that will act as a reference point for the drone. And here's a video that will show the working of this algorithm. Sorry. Okay. I think it's visible. Drone in GPS when it has the access to the GPS. And after it takes off, I have already set the EKF source, second EKF source to not using the GPS and already relying on the external position estimations. So when I turn off the GPS and change the EKF source to the secondary EKF source, where it do not have access to GPS, the drone will start to take the camera frames, match it to the already existing map it has, and it starts to localize itself without the GPS. So I will just, okay. I turned off the GPS. I started the secondary EKF source, and you can see the drone starts to move a little bit because there's a little bit of drift, but it keeps on correcting itself. And right now, I can even use the loiter mode to actually control the drone. That I will do right now. Just a second. Yeah. So in the loiter mode, even I can control the drone without the requirement of the GPS. So that kind of acts as a positioning system for the drone, this SIFT. But the only major problem that I discussed earlier is the rate we need to get, the minimum of 4 hertz. That's really difficult to get with SIFT. So why not use it with some other approach that uh, yeah, why not use it with some other approach that can give us a rate, the position rates at a higher position rate. We can get the position at high rates, and the feature matching will work alongside it so that it corrects the drift from that thing. So best approach would be using the optical flow. So if we use the optical flow, we can get higher rate position estimate, just directing it's getting the flow rates. And alongside, we can run the SIFT feature matching. So whenever it gets a good match, that's pretty much like it knows that it precisely is here, we can correct the drift over time. So in the optical flow approach, generally a very famous algorithm is Lucas-Kennedy method, which is generally used in most of the optical flow sensors already. So I modified it a little because the drone will be moving at very high altitudes. At low altitude, the optical flow work very well because there's a constraint in that at every consecutive frame, it estimates that the brightness of the pixel remains the same. And that's not the case, obviously, at high altitude. Sometimes drones will move fast, sometimes drone will be slow. So what I applied was a multi-scale pyramid representation. What it does is just when it takes the camera image, it scales it it scales it for multiple levels, smaller, greater, and greater, and it estimates the optical flow vectors for all these frames. So optical flow is nothing but just solving a linear equation after Taylor series linearization. So just solving the flow vectors equation for flow vectors variables from the equation and getting the flow vectors. So I get the flow vectors from all of these different scales, and I get a good estimation of the flow rate, and I can simply just dead reckon with those flow rates and use the onboard IMU to dead reckon that. Alongside that, what I can do is I can, on a secondary thread, I can continuously run the SIFT feature matching and run it until I get a very good match so that I know that the drone precisely is at the specific place. So what I do is, as soon as the drone takes off, I start the optical flow. The drone obviously work as an optical flow because of the multi-scale pyramid scaling. The drone can go at a very high altitudes already. So after high altitude, it starts to drift a little bit. But because the drone already has the map and it finds out a match, there's a Loess ratio loss ratio test, which estimates if we have a good position system. If I get SIFT features for, let's assume, greater than 30 points. So I know that it's a good match. So as an example, this image at bottom, not so good image, but yeah, let's assume the drone needs to go at the straight path that has written the actual path. But because the optical flow is turning, there's obviously a drift. It starts to drift a little bit to the bottom side here. And at the middle, let's assume the feature matching find out the absolute position. Okay, so I'm drifting a little bit. It starts to averaging out the values that it needs to be plus where it is. It starts to correct slowly to where it needs to actually go. So kind of just merging this to the high rate estimation of the position plus the low rate feature matching for an absolute positioning system, I can get a reliable system for the optical flow implementation for this implementation specifically. And there's a small video for that too, this implementation also. Uh, Okay, so as the optical flow drone starts to move, these optical flows, these are calculating the flow rates. And alongside on the secondary thread, a SIFT feature matching is also working. So as soon as the drone starts to drift, currently it's in the non-GPS, it do not have an access to GPS. So SIM GPS disable is turned on. So it's not having the GPS right now. So as soon as it's moving, I am commanding it in loiter mode. As soon as it starts to drift and it's find a good match on the map, it starts to correct itself over time so that it does not drift a lot from its actual path. So the result from the optical flow and the feature matching seems pretty reliable. And obviously, these things work very well. But the thing that we have not considered are the clouds, are the water, or the area that do not have very much specific feature points. So specifically, the main challenges in the vision positioning system, the traditional algorithms of the VPS positioning systems, is that first of all, resolution, angle, and lighting will not be same in every case. You made a map today. Tomorrow there will be less light. There will be different perspective of the camera. There will be different lighting. And obviously, this thing won't be working with the satellite images because it works generally on the intensity of the pixels, just the change in the intensity of the pixels. So these things won't be reliable in the case when we have a satellite image or there's a lot of changing in the resolution, angle, or lightings. Second, again, as I mentioned, clouds and water reflections can cause inconsistencies in visual data. If there's a cloud cover and the drone is flying really high, it won't be able to see the every part of the terrain. So it won't be working that way also. Plus maintaining a consistent high rate, as I mentioned with the SIFT, the 4 hertz. It's really difficult with the SIFT because it takes a lot of memory. So what can we do in this situation? So the best friend, the AI, the transformer model, the recent release, the chat GPT and all, the transformer model that they're using, that they have changed everything regarding the AI space. So what the neural networks can do is instead of matching all the specific pixels on the very basic mathematical equations like Laplacian of Gaussian and to find the edges and to find the estimations, it can just get a smaller part of the image from the cloud cover. It can, using the neural network, it is trained on the transformers. It can find out exactly where it is without having to rely on to get a very specific, good, clear image for that. So how does that work actually? So let's see for the transformer. So I won't be giving too much, won't be discussing too much about the vision transformer, but as a basic thing to understand how it works is, for example, we have a input image of satellite image, not the map. Right now we can use Google Maps or anything that can give us a satellite image, or we can just download a satellite image from Google Maps or anything. We can get the satellite image, store it on the companion computer. So what does the vision transformers actually do? It converts the image into small patches, and it takes each of the patch, it converts them to a mathematical number, which we call the embedding. So just for the computer to understand, it creates a multidimensional array or the multidimensional embedding the mathematics in the numbering thing. So let's assume it gives each patch as a two-dimensional embedding, a value. It's just a mathematical number. And the main thing about the vision transformers, this specific model, is the self-attention mechanism. So what it does is, if, for example, I have a satellite image and I have a drone image, it tries to find out the cross correlation between each patches. So for each patch in the first image, patch is just small part. And for each patch in the second image, that's what I'm getting from the drone. I found the cross correlation between each of them. I get a number. So the closer the two numbers are, the two patches are more similar. If I explain in a very simple manner. So if I have a specific place over, for example, a building, I get that patch from the building on the image, the vision transformer will get. It will get that specific patch from the map. It will try to find the cross correlation. And the best thing about this, we have a relative numbering in that. In case of SIFT, we do not have any relative system for that because the SIFT is just some mathematical equation giving us if it's a good match or not. But here because every patch is cross correlating with each other patch, we have a specific number for each a specific number, which defines the relativity with the other patches also. So when the two patches have the very close number, like for example 33 and other patch has the 32, obviously it will be an n-dimensional array, just to simplify the things. One has a number 33 and the other patch is 34. So I know this patch is correlating with the patch on the satellite image. So I know the drone, precisely where the drone is right now, because the numbers matches a lot. And if I am able to do that, obviously I can localize the position. And because the vision transformers right now getting so fast, I can easily get the rate of up to 5 to 6 hertz. And if I can just optimize it a little bit for a specific use case, I can easily get up to the 10 hertz. So as I mentioned, the global view and all these focusing on important features because it's cross correlating between multiple patches already. So I think the implementing the vision transformers seems a pretty good call for this thing. So there are actually two very popular already available transformer models, vision transformer models. So the first one is jitter. So this is a detection transformer. So what it does is, so the first approach, what we can do is, if we have a satellite image, we can run the data. So just think about it, some object detection, the data, but it at the back and it using transformer models. So it can detect, okay, there's a building over here. There's a static like road over here. There's this other kind of building over here. And it can look in the map also. The satellite image, it can find out, okay, I have this pattern. The building is here, the house is here, the car is here, something specific is here. And I can same find match that to the satellite image where that exactly is. The first analogy that I mentioned, the village analogy, and it's literally working like a human eye would work. It will find the same pattern of the buildings where each being placed. It finds out on the secondary image, and it can easily localize itself because it knows I can find this pattern in this specific area. So the data works that way. The only problem with the data is that because it's the object detection only. So it can only classify the buildings at all. So two buildings can be same. If we are in a kind of, we have the multiple buildings over there, this won't work because it cannot classify how the one building differs from other. So we might have something much better than data, and that is Lofter. That is local feature transformer that work pretty well to match the satellite images. So instead of detecting the objects like buildings or just car or a pond or anything, what it do is it just uses it stops at the part where I just mentioned, like the cross correlation and the number. The moment it gets the cross correlation between the two patches of the image, it finds out, okay, these two numbers are pretty close. The two n-dimensional tensors are very close to each other. It stops there. It tells, okay, these two patches meet. And again, what the SIFT does, it do with the data that it is trained on. So instead of, because SIFT can only SIFT and other like orb and all other these mathematical feature estimations just can only do when there's the can only work when there's no significant change in the scale. The scale does not change a lot and all these things. But here, because I can do the course level feature extraction as well as the finer details also. Plus, as we have the positional encodings also in the vision transformers, we can easily find out where exactly the drone is because we know the position on the image. We can easily localize itself there. And we have a relative confidence-based matching refinement, which is not available in the other cases like SIFT and all, this basic algorithm. We have a specific relativity. We can find out how much this patch relates to the other. The only problem with this thing is the data. The data for to train these transform models this requires a lot of data actually. So to actually get that much data and to train it on is really a challenging task. So I and Rice are already trying to get the data for this to train it on. But let's see how it goes. But overall, the Lofter works the similar way. It finds the unique features, it correlates each other, and each matches the key features and find out the location. So this is just an image. I have not tried it very much with the videos. So so one is the satellite image, and other one is the actual image from the drone. It pretty much is able, and very low data. It's just trained on few thousand images. It is able to find out, match the positions on the satellite image where the drone currently is. And we can again just use the same analogy, like we can find through the pixel values where the drone is in the local coordinate frame. Overall results, SIFT proved to be highly reliable. The only problem with the SIFT was it cannot provide the data at very high rates until it is compressed a lot. And after it is compressed a lot, the problem with that is it does not find all the features precisely. The optical flow is good, but the drift it adds, plus these cannot work in the cloudy environment or in the environment that do not have too much features. So these can be enhanced using Lofter or these transformer models. We can even construct our own transformer model architecture, and we can easily map the complex environments. So what could be the next would be just making an architecture for the vision transformer specifically for the use case, because there's a lot of research is already going on this part. So there are some companies already which are working, which are just using the SIFT or some other algorithm. But the only thing they are not yet able to find out, again, the cloud cover, they cannot fly over the cloud cover, and they generally it works very well. The SIFT works very well in kind of in planes, because planes can dead reckon for a lot longer as compared to the copter. So they can easily use the optical flow. They can easily dead reckon and use the SIFT feature matching to actually localize them itself. And we can implement this EKF resets over a long time. So there's an EKF reset command which can be used to reset the EKF when it's drifted a lot. So Lofter and all this can use this. So that was all from my end. And thanks a lot. So if there's any questions.
Have you given any thought to being able to search features if you need to find your position again after a long period of cover, or if you don't know an initial guess?
Yes, we can. Yes, if we do not consider the time in that case, in case of SIFT, which I tried a lot. So if we do not have the initial guess, but the overall perspective, the light change, as I mentioned, are not changed a lot. The very first guess will take at least a second or 1 second, a second or two to at least get the initial guess. Then we can use approximately nearest neighbor algorithm. So it do not searches the whole image continuously. It keeps on searching the local area as the drone moves. So the initial case, if you do not know where it is at the beginning, it can take a second or two, but later on it can start to produce the data at 4 hertz or 5 hertz.
Thank you for an interesting talk. I wanted to get more of it for which altitudes this can be, or like what will be the lower threshold?
Okay.
Um,
So this optical flow, because it's optical, it can start from a few meters also, because the optical flow works at that distance only. But up to on the simulation part, I tested it up to 150 meters already. Above 150 meters, it starts to actually misbehave because of the features and the cloudy thing I have added the cloud in the simulation. But the lofter part, which I tried with the cloud cover, a little bit, I don't have photos, I guess, but yeah, I tried it with cloud cover, which has a very minimalistic view of the actual terrain, and it was able to precisely find the location within a meter or two where the drone is. So yeah, I think it will obviously, the lofter and this transformer model, I think, will work up over 150 meters also of altitude.
So if I understand you correctly, the lower altitudes are less of a problem, or more, are the lower altitudes less of a problem?
Yeah, lower altitudes are less of a problem. You're right.
Okay, thank you.
Yeah, so thanks. First of all, thanks very much, Sanket, for your work. I think it's really great, and it's a feature that we hear a lot of people want. And I think you've done a great job at sort of setting the roadmap, at least, and more, I think. One question is it when you're using the visual transformers, is it important to make it easy for those transformers by, say, for example, rotating the drone's, live, picture or video so that it probably matches, say, for example, like Google Earth's maps? Or, another idea would be, I guess, is it important to, zoom in or out, I don't know, the pictures from the map to match, what the drone is seeing? Is that kind of, simple transformation helpful before you pass them into the visual transformer?
That can actually help. But the thing with the visual transformer is they find the gradient for each of the patch that they get. So they know what the orientation is, and it automatically, using that self-attention mechanism, it find out where it actually is. So the transformation would obviously just might help us with the making it a little bit faster. But I think the vision transformer can work pretty well with the different kind of transformations already.
Cool, thanks.
Hi, Sanket, great talk. We heard some benchmarks as to, SIFT was giving you trouble running at higher rates. What sort of architecture were you running this on? What are those benchmarks based on?
All right. So for the simulation part, I tried it on, I used a GPU-based SIFT also and a CPU-based. For the CPU-based, it was i7 12th generation kind of CPU, and for GPU, it was RTX 4060. So on the CPU one, I was getting barely around 4 to 5 hertz. And with the GPU one, though GPU one does not work really well, but yeah, I was able to get up to 6 to 7 hertz. Sometimes when it's transversing, but sometimes if you do not find the match pretty well, so it just decreased up to 1 hertz or 2 hertz in that case. But on the, if we test, I have tested on a video on NVIDIA Orin NX. So I got up to 4 to 5 hertz on the NVIDIA Orin NX with the GPU based SIFT. But that also depends upon if the clear view of it, the drone is getting a clearer view of the terrain or not. So it can range anywhere between 1 to 5 hertz. So yeah.
And this is a standard OpenCV implementation.
For the SIFT based, the CPU based SIFT, it is a standard based. But for the GPU based, I have made it modification because the existing GPU based SIFT does not really work with the Python, or even in the C++, does not really work well. So I made some minor changes to SIFT so at least it can scale the pyramid, as I mentioned, the multi-scale pyramid. I implemented that on this GPU-based SIFT. So at least I can get a much reliable position because the GPU can work on a much higher rate. Yeah.
Thanks.
日本では結構山とか田んぼとかってあるんですけども、私の方では産業用と、農業用の、ドローンを作ってるんですけども、その中で、田んぼだと同じフィールド、同じ模様なんですが、そういったものの中で GPS がロストした場合、あと山間部の、マウントとか、そういった変化がないようなところでの、位置の精度とか、それが知りたいなと思いました。ぜひ、すごくいいアイデアなので、検証してみたい。
Sorry. Yeah, so the question from Murata-san is, here in Japan, we have a lot of mountainous terrain. And also, I believe his company works on agricultural drones, and they're often flying over rice paddies, which are very similar. And so he wonders about, how good the quality is in those situations.
So specifically in mountainous areas, specifically in mountainous areas.
Mountainous areas and also areas where, could be rice paddies that all look very similar. And how does the algorithm work in those situations?
Okay, so if the features are, yeah, so in that case, if the features are already very same, like the paddy field, so it won't be working really well in the paddy field because obviously it cannot distinguish between if the specific patch differs from other patch. But in case of the mountainous areas, if it's flying really high, that then probably might not be your question. But yeah, if really flying really at high altitudes of the mountains, that can really work well because we have the terrain SRTM terrain data set also available. So we can actually map the positions from that, and we can actually localize our mountainous areas also at high altitudes.
Thank you. ありがとうございます。
All right. Thanks a lot, everyone.